Hey, I'm James with the Garland County Library, and I'm excited about the privilege of presenting an exciting program for my alma mater, the Henderson Chemistry Club demos. I graduated from Henderson State University with a degree in chemistry in May 2020, and I'm just really fired up about this. So, part of being a successful chemistry major or any science major is participation in the chemistry club, where good members will help raise funds and they participate in outreach opportunities. And the funding goes to undergraduate research presentations at the National American Chemical Society meetings. And that's just a really big deal for aspiring researchers. So, with no further delays, here's a chemistry club demo night.
All right, well, good evening. I'm Dr. Campbell, one of the main advisors for the Chemistry Club. And I thought we'd start off tonight with something that's fun and everybody likes to see, a little fire, color of fire here, and we're going to light it in just a moment. I'm going to light up a Bunsen burner. And then I'm going to shoot some solutions of different metal salts into this flame, and we're going to see what happens. And what we're going to see is colors, and the colors are going to be produced by the electrons that are in these metals being excited to higher energy levels. And you know, when you get excited about things, when you're all done being excited, you like to relax a little bit. And that's what happens with these electrons. They go from a high energy state to a lower energy state. And when they do that, they have to give off energy somehow, and we're really privileged that they give it off in the visible light range. So let's see what happens. First, goggles, because we play safe here. All right, let's see if I can get a flame. Looks pretty good. These little traces of yellow that you see around the edge there are from residual traces of sodium. Sodium is literally everywhere. We have sodium ions on our fingers, in our saliva, in our spit, in our sweat. So it's really hard to keep sodium away. But sodium produces that yellow color that we see everywhere. And so we turned off the lights, which is going to make it interesting for me to see. But I'm going to try a little bit of potassium salt here, see what we might get with a little potassium. It's a harder one to see, and now we have the wall on fire, but that'll go away soon. So I'm not worried about that. Here's one. This is lithium. Now, color. We'll put it up here in the air a little bit. You can see it. Shoot in down closer and get some really strong reds going on. And these residual sparks here you can see are from a little bit of the lithium solution still in the air. And next up is copper. Now, copper you're probably familiar with because it's sometimes sold as an additive to make fireplace flames. It gives you a green or sometimes a greenish blue. See if I can avoid setting the wall on fire this time. So there's a little copper for you. And then we have another metal. This is called strontium. It's a little less common than some of the other ones, but still very important. Another brilliant red one. It just impacts my eyes, makes me want to squint. It's so beautiful. Now I have to wait a little bit for that to boil off. Then we're going to try boron. Now, boron isn't actually a metal, but it's one of the few nonmetals that behave similarly in that it will allow us to also see colors. Most of the nonmetals don't really cooperate, but boron, this is boric acid that you could buy at the drugstore. Really pretty green there, a little bit maybe yellowish green. Some of these are pretty obviously got sodium contamination. And now we're going to try a really tough one. This is a metal called indium. It's in the middle of the periodic table. Not exactly in the middle, but close to the middle. And it under good circumstances, will give you a really blue flame. I promise. So does my burning methane here. So we'll see if we can get it to view. You see a little bit of bluish, sort of a lilac color, I guess, there. There's a little blue. It's one of the hardest ones to demonstrate. Part of the issue with indium is the salts have very low solubility in the solutions that we're using. So there you see it, some different colors that we can produce from exciting the metal ions, putting them in high energy situations and letting them relax and give us some light. All right, speaking of light, next up we have Rocio and Sarah. And we'll let them talk about it.
Hi, I'm Sarah, and this is Rocio, and we're going to be doing an experiment called the elephant toothpaste. And what you're going to be using is, this is something that you can actually do at home. And this is 3% hydrogen peroxide. It's something that you may find in a first aid kit or something like that. It's because it is actually very toxic, because if you have an enzyme called catalase, this enzyme creates oxygen and water through this hydrogen peroxide. And you use it on cuts or scrapes, because when you have a cut or scrape, you may have an anaerobe. So this is a bacteria or some sort of germ that cannot survive in oxygen. So when you use this and create a bunch of oxygen, it will kill out the bacteria. And that's why you can find it in a first aid kit. What we're going to be doing is something very similar, but not to kill any bacteria, but to do this reaction called the elephant toothpaste. And so what you do is you put a little bit of dish soap in it, or you can put a lot too. And we're also going to be putting some food coloring in it, so you can see this really pretty color when it starts to do its reaction. And what we have is actually around 3 grams of yeast, and you can see it in these little tiny pellets. You can actually get this yeast just from the store if you're making bread or something like that. And we already have this already made, and you put it in hot water. And what this does is that it makes it almost look like a melted ice cream texture. And what this does, it does a small reaction. In this case, it's doing a much smaller reaction than we would see. But here it is here. It makes this little tiny foam that we see here. However, if we do it with a different type of another catalyst, which is no longer we're using catalase, we're going to be using iodide. And it's an ion that when you put it inside the hydrogen peroxide, it does something much more like this. So this is the yellow one, and you can actually see that there's some, I don't know if you can see it, but there's actually steam coming off. And this is because this reaction is very exothermic. So we could see all the steam coming off, and it's a really exothermic reaction. And I don't know if you could see it through the camera, but when it starts reacting, it might turn a little orange, and that's because the iodide that we use actually becomes iodine. It's having its own reaction at the same time, and that's actually used as the catalyst to make this. So you can do a smaller version with the yeast, but you can also do a larger version if you have access to iodide, which you may not since you're not allowed. So after this, we're going to move on to a different experiment done by Joseph Andrews.
Hello everyone, so today we're going to be using these drugs to make the whoosh experiment. So what we're going to do is we'll use either methanol or propanol. This one's been preloaded with propanol to conduct the experiment. But here we're going to add the methyl alcohol, okay, methanol, to the jug, and then spread it throughout the inner surface area. Make sure you get it even and nice. So what's going to happen is the methyl alcohol will kind of evaporate inside this jug, and then we want the evaporated particles to stay in here, and then we can light them on fire to produce this experiment. Alright, so first we'll try the propanol. Keep it a safe distance. Good camera angle.
Maybe go a little bit. There you go. That's good.
Alright, if you want to turn the lights. Oh no. Well, this one was kind of a dud. It's just on fire now. But since this one was just made, it should have a little bit more reactivity to it. And there goes the whoosh experiment. Let it burn out before you go after it. That's all I gotta say. Okay, so. Oh. Okay, the pickle. Okay, so now we're gonna go to the pickle experiment.
Hi, I'm Joseph. So what we have right here is a set of 2 nails stuck into a pickle, completing the circuit that we make with this alternating current converter that's plugged into the wall. So normally whenever you have a circuit like this, if we didn't have a pickle in there, it would simply allow the electrons to flow through without any problems. But since this pickle and these LEDs are in the way, it is going to steal some of the electrons and use it for some other purpose. In this case, the LEDs are going to light up, and the pickle, the salts inside of it are going to steal some of the electrons in order to become more stable. And whenever it does this, it'll start to light up, causing a very intense glow. And we are going to demonstrate that now. As you can see, that one starts to light up, and it just burnt out because it had too much power. And now, as you can see, and so as you saw, this LED started to light up very intensely until it stopped. That's because these little LEDs aren't rated for that much power. So it just burned out because the metal inside of there just could not handle it. But now we are going to transition to Caitlin, and we're going to be doing her comfort chamber.
Hey guys, so I'm going to do this demonstration first, and then we will talk about what's going on. Okay, so this is the gummy bear torture chamber, and this reaction, not as bad as it sounds, is just a simple combustion reaction. And in a combustion reaction, there are 3 really important components. 1, heat, 2, fuel, and 3, oxygen. And so within the tube, within the tube is potassium chlorate. And when it decomposes from the heat, it produces the oxygen. And that oxygen reacts with the gummy bear, which is the fuel, to create the combustion reaction, which we saw in the tube. And the heat and fire that you saw is due to the fact that the reaction is an exothermic process. So I'm heating up one more tube for you guys so that we can do it again, and then we'll see it one more time with a different gummy bear this time. Taking a little bit longer than expected. Almost there. Oh. Okay. All right, so there it is, the gummy bear torture chamber. So now we're gonna move downstairs. We're actually going outside because we have a liquid nitrogen experiment that we're going to do. So right now we're about to take the elevator downstairs. We are heading outside to Dylan. He is a senior at Henderson. He's going to be graduating this spring. And he usually works in the inorganic lab. And what he usually does, he does his research in the inorganic lab, and in the inorganic lab, they have liquid nitrogen that they use. So liquid nitrogen has some really interesting properties. I'm going to let Dylan talk about it, but we're going to see some really cool experiments through with pressure change, temperature changes, and we're also going to be seeing a liquid nitrogen rocket. So we're about to go outside. He looks like he's going to be about to be ready. And I see him outside waiting for us very patiently. Thank you.
Hello there. Okay, so long way. So my name is Dylan Hubbard. I'm a senior here at Henderson State University. And plan to graduate this semester and go on to medical technician. But today I'm going to show you something fun, some liquid nitrogen. Something you should know about liquid nitrogen: it boils at minus 196 Celsius, which is about minus 330 roughly Fahrenheit. So, and water boils at about 100 degrees Celsius. So a difference of 296 Celsius. So to scale, if you were to the difference in temperature being about, it's like if you boil water at almost 500, 400-ish Celsius. But the first thing I'm going to show you is how the pressure, or really the gas loss. So out here, it's probably about 50 degrees out here. So this the air inside this bottle is about 50 degrees Fahrenheit. But as we put it in this liquid nitrogen,
the temperature inside the bottle will go down, thus decreasing the pressure inside the bottle. So the bottle will condense. And atmospheric pressure will account for the pressure that this bottle cannot make up. So as you get it in there, it completely fills up. And as we close it back to the air, the heat of the air heats back up. We'll get our bottle back. We'll throw some of the water in there too. Hopefully that doesn't blow away. Pour some of this back in here. Now something fun also, since in flowers and leaves and whatnot, there's some water in there. As the ice, or not ice, but the water in those flowers, as they freezes, it becomes rigid. And that rigidity will cause the spatter. Let's see if we can get this done. Let that set for a second. See if we can come down. It's getting there. Oh, it doesn't break up too much. We have another flower if it doesn't do it right. That'll work pretty good. Okay, I can pick it up. So now, drop it. Yeah. It just shatters as though it was glass. So that ice in there doesn't allow the flower to bend like it normally would. Now, the next demonstration, you can help me with it. We're going to be, the idea is it's a rocket of sorts. So, the amount of energy that it takes to boil liquid nitrogen, about 7 times less than that of water. So usually it takes around 40 kilojoules per mole. Boil water. It takes about 6.86, 6.7 kilojoules per mole for nitrogen. Now, the idea that we're going to be using here is the specific heat of water, about 4 kilojoules per gram, or not gram, 4 kilojoules per mole in Celsius. So as the liquid nitrogen wants to cool this, so it'll evaporate rapidly. Out of that. Take a good shot.
So right now they're pouring liquid nitrogen inside the funnel to go into the bottle that has hot water. And because liquid nitrogen is more dense, it's going to sit on top for a little bit. But as you see, once they turn around the bottle, there's something happens.
That didn't quite work how I wanted it to.
So that one exploded, and do you want to show them the smaller bottles?
Yeah, we do have a smaller bottle.
So that was a little more explosive than we thought. Definitely more explosive than how we practice. Yeah. But we can also show it in a smaller bottle, and it should go in the air. That one blew up the bottle.
Yeah, this one got a little bit more reaction.
That's okay though. All right. So to put it in there, we'll use a starter that actually looks pretty good. That should be plenty. All right. So, bottle here. So it's something. Hopefully. Yeah. All right. Okay, take two. Gases at atmospheric pressure, they take up about 1 mole is about 22 liters. So it expanding that fast is what caused this to explode. It had nowhere to go. It was trying to get that water out, but couldn't quite do it. But so
So
that's it today. At least that I am here.
thank you for being with us. We can see all our participants that helped us do everything. And I want to thank you for just being here with us. Thank you.